Okay, so as I said, there's effectively three parts to this talk. The first part is a tutorial, a bit of introduction to theory, a description of the different kinds of IFUs you're going to come across, useful overview information, but not so much emphasis on the practical side of things in there. Second part is a hands-on tutorial. We're going to reduce some wife's data. If everyone has downloaded the files that we were supposed to grab before the start of this workshop. The relevant section, I think, is just called wife's IFU demonstration, unless it got renamed by the organisers, but it should be fairly obvious to find. And that should take hopefully about 45 minutes. And then I'm going to finish up with a bit of a summary, a bit of tips and tricks, a bit of these are things that didn't fit into other parts of the discussion, but are still useful to know. Feel free to interrupt at any time if you have any questions. It's very much not a formal talk, but an interactive thing, so anything that's unclear, anything you found in your experience that you didn't know how to do, but would like to know how to do, interrupt at any time. Okay, so first couple of slides are just going to be on useful tools or places to go to look for more information. The first one is a set of websites that have interesting things about IFUs. The top one is the Integral Field Spectroscopy Wiki, which used to be a very well curated resource describing essentially all of the integral field instruments that are available anywhere in the world, their properties, what telescope they're on, useful things for reducing their data. It's not so well maintained over the last maybe 3 or 4 years, so if there's a new IFU, that may not have appeared on there. If the dead reduction package has changed for an IFU, that may not have appeared on there either. But generally it's a good first place to go. It also has a lot of general recipes, the kind of things I'm going to be covering in this tutorial actually, on the general principles behind reducing IFU data, general data reduction pipeline packages, links to specific instrument pipeline packages. So if you have a relatively general IFU question, that's a great place to look. The next obvious place to look are instrument-specific sites. So these are listed here for most of the IFUs you'd be using as an Australian astronomer. There's obviously other instruments on VLT or other telescopes that you could get access through collaborators or Open Skies time, but I haven't listed all of the instruments. Again, go to the IFS wiki if you want a complete list. Instrument websites are very useful. They tell you about the instrument properties, very important, different fields of view, spectral ranges, all those sorts of key things for science, but they generally also tell you how to prepare your observations. Integral field observations take a bit more effort to prepare than most observations, I would say, but I'm not going to be talking about that at all today. And they generally provide access to the data reduction tools, the calibrations that are necessary to reduce the data, some analysis tools as well, perhaps. And possibly most importantly, they'll give you the email address of the instrument scientist, so when you inevitably run into problems, you'll know who to contact. And then down at the bottom, these are just websites for some integral field spectroscopy surveys. The data here is generally publicly available, or soon to be publicly available. So even if you don't want to take your own integral field observations, you might want to do science with integral field data. The surveys, those are all galaxy surveys, I apologise, that's my background, but that does seem to be where most integral field surveys are targeted. You can do the science without taking the data yourselves. It also is a great place to look at the kinds of integral field data you get. There's quite a range of instruments in there that provide different spectral wavelengths, different resolutions, coverages, fields of view, slightly different output formats as well. So that's one of the challenges of IFU data. And again, a lot of analysis tools can be found on those websites as well. So second slide here is a list of useful resources. The first thing to do when you have some IFU data, you want to be able to look at it. Having FITS files on your hard drive that you can't do anything with is no help at all. I assume most people are familiar with DS9, just opening general FITS files, images, spectra, whatever. Some people like FITSView or FV, I'm not a fan personally, but many people do enjoy it. It's a bit more lightweight than DS9, so easier for opening images, but less useful once you've got them open. The one you may not be familiar with, which is IFU specific, is QFITSView, which is an IFU cube viewer. DS9 is great at displaying images, but IFU data is three-dimensional, and DS9, though in its latest iterations has become a little bit more IFU friendly, I still don't think it's the best choice for this. I'm going to show you some things in QFITSView later on. If you don't have QFitsView, you may want to download it either now or when we get onto the tutorial section or the hands-on section, just because it's a very useful way of looking at IFU data. The other section here, data reduction tools. These are sort of general tools that you can use to reduce your IFU data. I have attempted it in IRAF. It's not much fun, but it can work. Python or IDL are a bit more flexible, less tools prepared for you in advance, but generally IFU data is sort of modern, and IRAF is not. So a lot of IRAF tools are not well suited to IFU data anyway, so if you fancy a challenge, then starting from scratch with Python or IDL or any other programming language is fine. P3D is an IDL, I believe, based general IFU data reduction package for fiber-fed IFU specifically. I'll come on to different kinds of IFU in a few slides, but it's not instrument specific. It claims to be able to reduce data from any kind of fiber-based IFU instrument. Whether that's true or not, I haven't put to the test in any meaningful way, but it has been used for a number of instruments, and I think the Khalifa survey also based much of their data reduction on the P3D package, so it certainly works for some instruments. And then, of course, there are instrument-specific packages and pipelines that you can find on the instrument websites, and that would generally be the better way to go. As an interesting aside, many tools that have been developed for radio astronomy can also be applied to integral field data. Radio astronomers get cubes, position, wavelength. IFU data is cubes, position, wavelength. So not so much on the reduction side of things, but certainly on the analysis side of things, something like fitting velocity fields, fitting galaxies in 3D. A lot of tools have been developed for radio astronomy. There are also many optical tools as well. But don't just, if you look up astronomy data cube on Google and the first site you find is radio astronomy, don't ignore that website. It may have useful information for you. So as promised, I'm going to talk about the different kinds of IFU now. There are many IFUs now over the last 15, maybe 20 years. IFUs have proliferated, but they fall into three broad types based on their construction. You have fiber-fed IFUs, where you use optical fibers to take the individual spectra from the telescope to the detector. You have slicer IFUs, where you're using an array of mirrors to essentially do the same thing. And then we have lenslet array IFUs, where in the focal plane you have a little sheet of effectively glass pixels that split up your image into individual spectra at that point. All three of these are essentially tricks for taking your three-dimensional data, position, wavelength, and arranging it on a CCD, which is only 2 dimensions. So that's the great challenge in integral field spectroscopy. You have 3 dimensions of data and only 2 dimensions of detector. And the way the different instrument designs solve this is quite different. But you always end up with 3D data at the end. So just to go into those different designs a little bit more in detail, fiber-fed IFUs. This is all SAMI data. Yes, that's true. This is all SAMI data. So for those of you who aren't familiar with SAMI, I guess Sarah probably talked about SAMI a bit on yesterday. So SAMI is a multi-object IFU. We'll ignore the multi-object part for the moment and just concentrate on the IFU part. This is what an individual SAMI bundle looks like. Each of these little things are optical fibers. Your galaxy sits here. For each optical fiber, you get a spectrum. So for each galaxy, SAMI is taking 61 spectra. These things lead onto cables that run down from prime focus, down the side of the telescope, onto the AA omega spectrograph in the basement. And then the spectra are arranged on the CCD like this. So this is a bit of a low contrast image, unfortunately. But you can see that there are basically lines running across here. Each one of those lines is the spectrum that's come from one of these fibers. They're kind of grouped, so there's a chunk of 61 here, a bit of a gap, a chunk of 61 here, a bit of a gap again. And you can see that there are smaller gaps between the individual spectra. So one of the great things about the fiber-based IFUs is you can arrange spectra on a CCD any way you want. Once you've plucked it off the telescope in a fiber, you can plug that fiber onto your CCD anyway. You can kind of have a random mess. Obviously, you want to make it simple, but the spacing is up to you. You can condense them all down and try and squeeze as many spectra on there as you want. If you want to have really high quality spectra and you're not worried about the number, you can spread them out a lot more, so there's no kind of crosstalk between them. They're very flexible instruments. They're very cheap to build. You guys probably don't care about that, but it does mean that you can get many spectra easily. There are a lot of fiber-based instruments because they are, again, cheap. And they can also take advantage of a lot of the multi-object spectroscopy tools. So if you were sat next door, you'd be hearing about 2D FDR data reduction. SAMI data reduction is very heavily based on 2D FDR data reduction. So the vast majority of the data reduction is just treated like multi-object spectroscopy. It's only towards the end of the data reduction process that you actually try and push everything back into a data cube again. And that's true of most fiber-based IFUs. Another example would be GMOS, so the Gemini sort of workhorse spectrograph. Mostly known as a multi-object spectrograph. Gemini multi-object spectrograph kind of gives that away. The University of Sydney insists that I have a virus scan on Thursday afternoon every week, which used to be a lecture time as well, so it's interesting anyway. Yes, right. Hopefully that won't interrupt us again. Where was I? Right, so you can take advantage of multi-object spectroscopy. So GMOS, multi-object spectrograph, most people use it in multi-object spectrograph mode. It does have an IFU mode, and essentially the data reduction is the same apart from the final steps. So a lot of those techniques you can apply to neutral field spectroscopy with a fiber-based instrument as well. Downsides. Fibers are kind of crappy. I don't know whether many people have worked with fiber versus non-fiber instruments very much, but you lose a lot of light going down the fiber. You lose a lot of light getting into the fiber, you lose a bit of light as it comes down the fiber, you lose a fair amount of light when it comes back out of the fiber at the other end. Yep.
So are they severely magnitude limited then?
I mean, in a sense, it depends how long you want to stare at stuff.
Yeah.
They tend not to be high redshift instruments. Most high redshift instruments use image slicers because they're much more efficient. We'll come on to that in a second. The fibers are getting much better, so the limitation is going away. But the downside to that is you're kind of trading the cost benefit versus the efficiency loss. When you get high quality fibers and you spend more effort getting your light into the fiber, that pushes up the cost of the instrument. So you always have the flexibility advantage, but there's certainly a trade-off between the cost versus the efficiency of fiber-based instruments that people have leaned towards generally the let's make it cheap and just get some spectra and not worry too much about what they are. 2D FDR, for instance, was designed as a redshift survey instrument, so you want a signal from as a 1 in 1 emission line per galaxy. So they weren't so concerned about getting good spectra there, they just wanted lots of spectra. So yeah, the limitation is becoming less of a limitation in the more modern fiber-based IFUs, but it's still there's a trade-off that people generally lean towards cheap and many versus a few good quality spectra. You're somewhat limited in how closely you can pack your fibers. So you'll notice here in this SAMI bundle, you have your circular fibers, but there are these gaps in between fibers. So this is a term known as filling factor. Effectively, how much of your image are you able to actually get down onto your CCD? For SAMI, the number is something like 70%. So of the light that's falling on this wider IFU kind of envelope, about 70% of that is actually making it to your CCD, and that's not including telescope and fiber efficiencies at all. Some of it simply isn't landing on a fiber, and that light is lost. SAMI actually does quite a good job of this. One of the big technologies behind SAMI is the ability to pack these fibers very close together. Manga, for example, the kind of American version of SAMI, is close to 40%. The GMOS IFU is lower than that. So you're limited in how closely you can sample your plane and how much light you lose between the fibers. SAMI actually has stronger limits on how close you can get bundles together. So fibers within a bundle are relatively closely packed, the bundles have to be very separated. So many people occasionally come along and ask us, oh, can I just put all of my SAMI bundles, 13 IFUs effectively, onto a single galaxy and map the galaxy that way? The answer is generally no, because you have to put the bundles so far apart that it's kind of hard to squeeze them onto the same galaxy. Saying that, you can avoid some of these limitations by coupling your fibers with a lens-led array, which we'll cover a little bit more later on. Essentially, you have your glass array of lenses, which you can pack very close together. They sort of spread the light out a little bit, and then on the back of your lens-led array, you can stick a fiber. So this gives you the close packing of a lenslet array IFU with the cheapness, relative cheapness, and ease of design and ability to put your spectral wherever you want on the CCD of a fiber-based IFU. Downside to this is every time you add an optical element to your instrument, you're losing light. So you're adding another optical element, you're adding, well, it's connected to two actually, you have the lenslet array and then the coupling between the fiber and the lenslet array, so these instruments are even less efficient. They tended to be ways of taking advantage of existing instruments in a new way. So the GMOS IFU, for example. GMOS was around before there was an IFU mode. People said, hey, we can turn our instrument into an IFU, let's make a lenslet array for it. But it's not optimized for that configuration. So they work, but they're not amazing. A few examples of instruments of this nature. I talked about SAMI, I talked about GMOS, Koala, also on the AAT. Sarah presumably told you a little bit about that. PPAC, which is on the Cala Alto telescope in Spain. Cala Alto? There's a 3-meter telescope in Spain that the Khalifa survey was done with. There's a few other examples as well. RSP is a fiber-based instrument that's on one of the US telescopes. So, lenslet array IFUs. Talked about these a little bit in the previous slide. What you're doing here is you're taking a physical array of lenses, putting that in your image plane, and using that to effectively pixelate your galaxy. And behind each of those lenslets, you effectively have a prism or a slit that's spreading the light out into a spectrum. This is the optical path for Sauron, which is one of the earlier IFUs. It's an instrument I worked on as part of my PhD, so it's dear to my heart. But it's a very nice graphic from this paper, the Cornell 2000, showing you how lenslet-based IFUs work. So here you have your galaxy, as you see it on the sky, with an interesting colour scheme, of course. Some telescope optics. This is what it looks like in the lenslet plane. So you see this grid square here is the grid of lenses. What these lenses do is they take the light from this region, focus it down into a single point. This goes into a prism. Each one of these points is spread out into a spectrum, which are arranged on the CCD here. So this chunk of light from here, I don't know if I fit on the screen, but there's a spectrum here, there's a spectrum here, there's a spectrum here. Each one of these spectra come from one of these little points. So lenslet array IFUs are kind of the intermediate situation between fiber-based IFUs and slicer-based IFUs. Intermediate cost, they're kind of intermediate efficiency, better than fiber, not as good as lenslet. They can be quite flexible in terms of how you arrange your lenslet array. This is the Sauron lenslet array. You can probably just make out the tiny little pixels here. Someone's fingers obviously showing you the size comparison. This is the Osiris lenslet array, or a graphic of it, as opposed to the actual thing. And you have multiple different configurations here depending upon the spatial scale you want to use. So again, optics before your lenslet array can essentially change the spatial sampling of your pixels. So with Osiris, you have a few options for a wider field of view, a narrow field of view with a larger spatial wavelength. And again, each of these lenslets can have different effective spatial samplings. You have from 0.01, possibly 0.02 on Osiris, up to 0.1 arcseconds per pixel, depending on essentially what you're doing here with your telescope optics. So lenslet array IFUs tend to be quite flexible, they're intermediate in efficiency, cost, those kinds of things. Get very high fill factor, so essentially all of your light that is falling on your CCD is coming from your image, is then put onto the CCD. You don't lose light between gaps of the lenses, there aren't any. So you have very high fill factor. You get square pixels, which is a surprisingly nice advantage. So in comparison to, let's get back, it's really hard. Comparison to SAMI here, where you have circular pixels, and this is an output image from SAMI. Circular pixels are kind of hard to analyze. You have to worry about, computers like arrays. Square pixels fall naturally into an array. It's not obvious how you express this in terms of an array. There are ways of doing it which we'll come to later. The square pixels are surprisingly nice. With lenslets, you can also not have square pixels. You can have hexagonal pixels, rectangular pixels. You can basically design your lenslet any way you want. So it's very flexible there. The downside to having a high fill factor is that you end up packing your spectra very densely on the CCD. As you can see here, there's very little wasted space. In some ways that's good, it gets you more spectra per CCD. CCDs are expensive. But the downside is getting these things back off the CCD can be quite tricky. You have to have very, very carefully calibrated where all of the spectra exist. And there's some overlap between spectra. They tend to fade into the background, but obviously this spectrum here doesn't stop exactly at this point. There is some residual light here. Similarly, there's some residual light coming out the other side as well. So densely packed spectra are harder to extract. Two examples I've got of that are Saron and Osiris. Finally, image slicer IFUs. So image slicers they use an array of mirrors. There's an example here. This is from Muse, which is the DLT, Fancy Musical Field Spectrograph. Each one of these things is a mirror. So what they're doing is your image, your galaxy comes in here, hits these mirrors, and is bounced off in slightly different directions. So it's going from an image where you have everything in 2 dimensions, you're essentially pulling off a slice, moving it over here, pulling off another slice, moving it over here, pulling off another slice, moving it over here. So rather than turning, like a lenslet array, turning your image into a bunch of individual spaxels, pixels, what you're doing is you're turning your image into a set of long slit spectra. So you can think of each of these slices that are coming down here as a long slit spectrum. That's good, because people have been doing long slit spectroscopy for a very long time. So once you have your long slit spectra, there are many, many tools for processing those, dealing with those, doing the sky subtraction properly, all sorts of good things. It also means that your pixels tend to be square or rectangular again. You're pulling off a slice. Slices have a Y column, effectively. And then within that, you're just putting stuff on the CCD, which has square pixels, and then you're taking it straight off in that fashion. Pros are, these are very high efficiency instruments. They only use reflections. The other 2 instruments we talked about have transmission between the surfaces. Either the lenslet array, your light passes through the lenslet, so the fiber passes through the fiber. Transmission is bad, reflection is good, it's higher efficiency. Lenslet arrays, slicer-based IFUs only have reflections, so they tend to be the highest efficiency instruments. These things are very complicated though, so that means they're very hard to build, which makes them very expensive. They have high fill factor, they pack spectrum to the CCD very efficiently, and as I said, you can use long slit techniques, so there's actually quite a lot of stuff for processing this data.
So, how are you able then to get the line of sight information if you're getting bouncing the spectrum and getting the slit?
Yep.
How are you retaining the lines?
So, forget about the IFU for a second.
Right.
Imagine we have a long slit spectrograph. What you're doing in a long slit spectrograph is you have your galaxy, you're taking a slit along that galaxy, so that's your one spatial dimension, and then you're spreading the light out this way. So you have 2 dimensions on your CCD, one of which is spatial, one of which is spectral. What you're doing with an integral field, an image slicer, you're saying, well, I'm going to take a slit here, put that on my CCD here, and I'm going to take a slit here, so I've moved down in, say, the Y direction, and then I'm going to arrange that next to my other slit on my CCD. So I have a long slit spectrum here, and then another long slit spectrum here, and another long slit spectrum here. Another way of thinking about it is, and in fact this has been done, if you only have a long slit spectrograph and a lot of time, what you can do is you can point it at your galaxy in one position, take your exposure, physically shift your galaxy 1 arcsecond, 2 arcseconds up, take another long slit spectrum, and then you can map your galaxy that way. That takes a really long time. So the image slicer is effectively a piece of hardware that lets you do that process, but in a single shot rather than in many, many repeated shots of moving the telescope.
And you're still having just the integrated, so in your XY, I have XY coordinate, at that pixel, I only have the integrated value, not the actual, at this energy range, I can receive this many photon.
So for each of your long-slit spectra that you create, you're spreading the light out in the spectral direction as well.
Okay.
So they're interesting in that this is an example of Weiss data. So this is your spectral direction. This is a spectrum. This is both of your spatial directions. So what's happening here is, as I go from here to here along a slitlet, I'm cycling along the x spatial coordinate, and then as I move to the next slitlet, that's a y jump. So that's from 0 to 30 something on y in x, y equals 1, and then this is from 0 to 30 something in x, but y equals 2, and so on. So yeah, you always have those x, y, lambda coordinates. It's just how you map them onto the sort of the x, y of the CCD that changes from instrument to instrument. Okay, so moving on to IFU data reduction. This I broadly divided into 3 main steps. First thing, general calibrations. These are pretty standard for all kinds of data reduction, imaging, spectroscopy. Effectively things you want to do to account for the fact that your telescope does not transmit every single photon it receives to your CCD. Your CCD does not convert every single photon it receives into an electron. It doesn't do that uniformly across the CCD. The general kind of flat fielding, bias, subtraction, those kind of things that you probably talked about in earlier parts of the week. I will cover those briefly, but those are non-IFU specific data reduction steps. Second step is the extraction of spectra. So you spend all this time carefully arranging your spectra onto your CCD, now you need to get them back out. This step is very instrument dependent, depending on which technique you've used to build your IFU. The approach you take to extracting your spectra varies strongly. So we're going to focus on an image slicer instrument in the hands-on tutorial, but I will talk a little bit about how that works in different IFUs as well. And finally, once you've extracted your spectra, you want to assemble them back into a data view. So this involves things like the wavelength calibration of your individual spectra, also figuring out where it is you got them from on the sky. So in this step, you want to know where your spectra are on the CCD, so CCD, x, y coordinates. And in this step, you want to figure out, I got the spectrum, where did it come from on the sky? So again, this is a little bit IFU dependent, less so than this step, certainly. There's 2 main approaches. Either you can take some kind of calibration frame, where you put a thing of known position into your IFU, observe it, and then map that back onto the other data where that wasn't in there. Or it's something that can be calibrated beforehand. So you understand your instrument very well, you know where on the sky a given part of the CCD corresponds to. So general calibrations, as I said, the goal here is really to account for instrument effects, CCD efficiency, going from electrons to photons emitted by the source. Not just photons received by the telescope, but photons emitted by the source. So flux calibration is in there as well. The things you're correcting for, CCD bias level. So I assume everyone knows why we put bias onto a CCD.
So there's always a positive detection.
Well, yeah. So essentially when you have an error, your counts are uncertain. If you start at 0, you can't have -1 counts on your CCD. So if your bias level is 0, your noise ranges from 0 to something above 0, it's asymmetric. If your bias level is 100, your counts then range from, say, 95 to 105. You subtract your bias level, your uncertainty is from -5 to +5, or whatever it happens to be in your instrument, so you have a symmetric error distribution. Symmetric error distributions make sense. Use it to the Gaussians, anything else is hard. So that's really why you apply a bias level. Dark currents, generally more of an issue with near-infrared spectrographs than optical ones. This is effectively saying, if I looked at this target for half an hour, how much of the light is not due to the target, it's just due to what's going on in the instrument. So effectively, during the day, probably, you stare at nothing for half an hour, and you see what nothing looks like. You do that over and over again, and then you subtract that from your data to get rid of what your instrument sees when it's looking at nothing. CCD sensitivity variations and illumination you kind of correct for at the same time. Sensitivity variations saying that, well, at the blue end of my CCD I get one electron per photon at the red end, my CCD is better, so I get 2 electrons per photon. I need to know that information so I can actually figure out how many photons I got rather than simply the number of electrons. CCD illumination is a similar but slightly different effect, and that's what you're accounting for here is how your telescope illuminates your CCD. So not all parts of the CCD are equally likely to get a photon that went through your telescope, as it were. Some parts get lost in the instrument, and depending on which part of the CCD you're on, that can be more or less likely to happen. So with the illumination correction, you're really saying, if 10 photons went in my telescope at this position, and 8 of them would hit the CCD, on a different part of the telescope, I would get 6 photons for every 10 that went in. I want to account for that effect as well. Cosmic rays, know them and hate them. Particles traveling through the atmosphere, hit the CCD, very high energy, they create electrons on the CCD, they're not things coming from the galaxy or star or whatever it is you're actually observing. But they're easy to spot. They generally saturate or detect instantly, they leave a little wiggly worm trail, or maybe just a single spot. Longer exposures, they're more of a problem. The longer you integrate, the more cosmic rays you get. Observing at redder wavelengths, they're also more of a problem. The CCD is generally thicker at redder wavelengths because the incoming photons are lower energy. You need a larger CCD substrate to capture the photons efficiently, which also means you have a larger target for the cosmic rays to crash into. But they're relatively easy to calibrate out in an effective fashion. It's only really at red wavelengths, very long exposures, they become a problem. Hot pixels and bad columns, these are defects in your detector. The way CCDs work is they tend to read out data along a column. If any pixel along that column is broken, you can't read out data from that pixel or any pixel on the far side of that pixel. So this then becomes a dead column. You want to see that this is actually a fantastically deep absorption line in your spectrum that you just discovered that nobody else had seen before. So again, you take typically a bias frame or a dark frame, and that will show you where they are. Many observatories provide hot pixel masks and bad column masks as well to just eliminate that data in advance. And then finally, the sort of overall calibration of photons from the source to electrons on the CCD, throughput calibrations. The way you typically do this is observe a source of known brightness, a spectrophotometric standard star, where everybody's observed it. It's been observed so many times with so many instruments, with very precise instruments that don't have many complications, that you know exactly how many photons that thing is producing. You then figure out how many photons you received from it, and that gives you a scaling that you can apply to your data to correct for this effect. These are the typical calibration frames. You're going to want to do these, bias and darks, flat, spectrophotometric standard stars. I missed half one. So when you're doing, no, I guess that comes up later, so I haven't missed. Most of these steps can be done early on in the reduction process. As I said, they're not IFU specific, they're generally the first things you do in the data reduction package. You get this out of the way while your stuff is just on the CCD, before you've even worried about it having spectrum on there most of the time. Though the throughput correction is typically done as a final step. Actually, IFUs have a big advantage here, but I'll come to why that is later on. Okay, so extraction of spectra. As I've said, the trick to integral field data is taking 3 dimensions of incoming data and arranging it in 2 dimensions of CCD. And different IFU designs do this in very different ways. Which means that you have to extract your data in very different ways as well. So lensless systems use what's typically called a rectification matrix. This is a file, a calibration file essentially, that says for every XY coordinate on my CCD, that corresponds to XY lambda in data space. Again, this is a Sauron spectrum on the CCD, so every single one of these pixels on the CCD, there will be effectively an image much like this, but rather than having a flux as the content of that image, it will tell you the X coordinate, the Y coordinate, and the lambda coordinate of that CCD pixel in data cube space. Determining those matrices is very hard, but almost always the observatory does that for you, and they update them as needed. They're generally quite stable. That's another advantage of lensless array systems, actually. They don't wobble very much. So pointing at different parts of the sky doesn't affect the instrument very much, which is very nice. Fiber-based systems typically use what's called a tramline map. So Matt's probably telling people about this right now. What you do is you put a lot of light down your fibers. Don't care about any structure in that light. You just want there to be lots of it and fully covering the wavelength space. So you have a lot of blue light, a lot of red light, and you get a map of where the light comes from the fibers. As you go down, this is a single wavelength slice from a SAMI tramline map. So what we're seeing here is these peaks represent positions of individual fibers on the detector. Here's a gap between the bundles. Here's another bundle, individual fibers. You'll notice that these don't go to zero within an individual hexabundle. So the spectra from adjacent fibers are overlapping, at least within a hexabundle in SAMI. That makes it somewhat harder to extract. What you do is you fit a profile to each one of these, you figure out how much light from this column effectively on the CCD to assign to this fiber, how much to assign to this fiber. It's pretty stable, but you tend to do it throughout the night. It does have the disadvantage that you don't know whether any given photon in this region really belongs to this one or this one. It's probabilistic. You assign the relative fractions.
It's probably not an issue, but you have to worry whether or not the light source is sort of saturating the fiber or not saturating the fiber. If you do like a complete Gaussian profile to diagnose the trend.
Yeah, you generally don't want to saturate the fibers.
Yeah.
It does make it harder to extract. You also, if you saturate a CCD, you tend to get spillover from the electronics as well. So then your fiber profile is no longer just the sort of optical profile of your fiber, it's the kind of convolution, as it were, of the electronics plus the optical fiber. So yes, the optimum is as much as light as you can get without saturating it at any point. Tens of thousands of counts, but not 64,000 counts. So most fiber-based IFUs work to a similar system. You trace the fibers with a calibration exposure. You work out where to assign light from a given CCD spaxel back to a fiber, and then you apply that to your science data at a later stage. Finally, slicer systems do something similar, but for slitlets. So they, rather than extracting individual spectra, extract their long slit spectrum. So this is an example of WIFEs. So this is the calibration frame that's being used to extract the data. This is a flat lamp, so there's not much spectral structure in there. WIFEs has an interesting way of doing its data, and only half of the CCD space is used for a normal sort of style of observation. Every other strip of the CCD is left blank. That's because WIFEs has a nod and shuffle mode, where you can effectively observe your target, move off your target to do a sky exposure, but shuffle the target one column over on the CCD as well. And then when you move back, you shuffle the data back over. So you don't have to read out between exposures, effectively. And you can do that on shorter sequences, so you get sort of simultaneous sky exposures. I tend not to observe in that mode. If you have strongly sky noise limited observations, then that can be a valuable thing to do. It does make your data reduction a little more complicated. This is an example of the nod and shuffle spectrum. So you can see that every other one of these has a star or galaxy in. These ones just have a sky data. So in this mode, what you're doing is, this is a single sort of slice through, say, this region of the image. You have flux here, no flux where there isn't a slit, and you want to extract the region where there's lots of flux. Slit edges, so it's not a perfectly kind of single pixel tapering, but you want to pick a region where you get most of the flux. WIFEs is nice because of these gaps, so there's very little crosstalk, effectively none, between adjacent slitlets. Many other slicer-based IFUs don't have these giant gaps. So again, this region probably wouldn't go exactly to zero in your data, but there'll be another slitter right here that goes up and down, where in this sort of intermediate region, light could have come from either the y equals 1 slitter or the y equals 2 slitter. Anyway, in a similar way, you figure out where your slitlets are on the CCD, and then you're using a calibration frame, and then you apply that to all of your science data. Final step is to take those spectra, or 1D long slit spectra that you've extracted, and reassemble them into a data cube. There's effectively two things you need to do to this. All spectra need to be placed on a common wavelength scale when you have a data cube, an array which has x, y, lambda as its coordinates. Each lambda slice has the same lambda coordinate for all x, y coordinates. So you need to take your spectra, which are not necessarily going to be all on exactly the same wavelength coordinate, and shift them, generally involving interpolation, so that for any given element of your array, all spectra in that slice have exactly the same wavelength pattern for that slice. The way you do that is effectively take an arc spectrum, so observe a calibration lamp with a series of arc lines. Those arc lines have very well-defined wavelengths, and determined very, very accurately in laboratories. So you have a list of line positions, line wavelengths, fit the lines in your spectrum, so you know where they are on your CCD. You match the positions of peaks on the CCD to the known wavelengths of lines in your line list, and that gives you a mapping between CCD spectrum pixel and wavelength pixel for every single spectrum. Then you interpolate your spectra onto this new wavelength, common wavelength scale. Second thing you need to do is assign each spectrum an XY position on the sky. Again, this is a little bit IFU dependent. As I said, for the lenslet arrays, it's generally done for you with the rectification matrix. For the fiber-based IFUs, this is again generally done for you by the people who build the instrument. The fibers are locked in place somewhere. In a SAMI hexabundle, they spend a lot of time figuring out exactly where all of these spectra are in relation to one another. So every fiber has a known physical position in relation to other fibers. You move the telescope around, of course, so each fiber can have a unique RA and deck at any given moment, but the difference between RA and decks at different fibers is what is known. And then the slices. So this is a little bit different. The Y position, so the column effectively that you've extracted the slice from is known. That's essentially a hard thing set by hardware. The positions of the mirrors, that's very well calibrated. But the X coordinates of the individual slices are not quite known. So slices can shift around a little bit on the CCD. So you want a way of calibrating which pixel within each slice corresponds to the same X coordinate. The way Weiss does this, and it's quite common, is to take a trace or a wire calibration, where you physically put a wire mask in your image plane. So you have a straight line in the image plane running along the x-axis. This blocks out light, so you get an absorption feature there. That absorption feature appears in all of your long slit spectra, and it appears at the same physical x coordinate on the sky, not necessarily the same coordinate, relative coordinate in each slit. You can fit the position of that dip. That gives you again that conversion from CCD coordinate system to physical on the sky coordinate system based on this calibration frame. So at that point you've got your data cube. There are a few optional extra steps you may want to take. You probably want to do some sort of sky subtraction. You can do that at the cube stage. You might observe your target, switch to observing the sky, make a target cube, make a sky cube, simply subtract the two, processing the sky cube in exactly the same way you might do the target cube. Talked a little bit about nod and shuffle, where you observe your target, keep observing, but switch to observing a blank field, so you get simultaneous spectrum, and then they're kind of interleaved like that, I guess. You have your object set, you have your sky set, and then you just shift and subtract. Often lenslet arrays have dedicated lenses targeted at the sky, so you have a set of lenses that are aimed at your object, and then just off to the side, you have a bunch of lenses pointing somewhere slightly different on the sky. You arrange your observation so that slightly different isn't pointing at another object, it's pointing at a nice blank area, so you get simultaneous sky spectra observed there. You generally want to do a little bit of calibration to make sure that your lenses that are pointing at the sky things have the same level of throughput as the lenses that are pointing at the actual object. Again, just observing a completely blank field, so getting sky through your object lenses and sky through your sky lenses is a good way of doing that. And then you just subtract the spectra from your sky lenses. And similarly, you can have dedicated sky fibers. So Sunny, for example, has its 13 hexabundles, but it also has 26 fibers dedicated to sky blank areas of the field, different parts of the instrument. So you get a sky spectrum, and you simply subtract that from all of your 1D fiber spectra that you've created. This can be done before or after assembling into a data cube, depending on which of those options you've chosen. Yeah, offset sky I would generally do after assembling into a cube. These other things can generally be done before turning the data into a 3D data cube. Flux calibration. I think this is best done after cube creation. Some pipelines do it earlier. The reason why is one of the big advantages to actually IFUs. If you're doing multi-object spectroscopy with single fibers, you put one of those fibers on a star, and your fiber is 1 arcsecond on the sky, and you're observing at the AAO, so you're seeing is 5.5 arcseconds, something horrific like that. A huge amount of your flux from your star is not falling down your fiber. You don't know exactly what the seeing is, so you don't know exactly how much flux you're losing from your standard star. That means that you can't actually rescale your flux particularly accurately because you don't know the true value. You don't know what was lost due to your telescope effects and what was lost due to the seeing being a bit crappy at that moment. IFUs, on the other hand, make an image of the star. So unless your PSF is horrific, or you have a very small format, small field of view IFU, you are getting all or nearly all of the flux of the star. So you can fit a PSF to the star, a Moffett profile, just a Gaussian, and that allows you to recover exactly the flux of the star that you observed, independent of the scene. That means you can rescale your observations very accurately as well. So IFUs tend to have better flux calibration than certainly fiber spectra, and often long-slit spectra as well. Long-slit spectra give you one spatial dimension on your star, but they're not quite. So if you have a somewhat elliptical PSF, if you're observing a high air mass, then IFUs don't care about that. Long-slit spectra do. Finally, you might want to combine exposures. You may want to expand your field of view, effective field of view, by arranging separate exposures next to each other. You may want to improve signal to noise by stacking exposures all in the same place. You may want to try and improve your effective spatial resolution by using sub-pixel movements of the telescope to recover some of that extra information in there. This can be done at or after cubing, depending on how accurately you want to do it and exactly what instrument design you have. If you just want to increase signal to noise and you're pointing to exactly the same place, then I would make cubes first and then combine them. If you're trying to dither and increase spatial resolution, then you generally need to do this before, or in fact, as part of the cubing process. That's a little bit complicated, so can stay in the sort of advanced section. Okay, so hands-on with WIFE's data. So my plan here is to mostly leave you guys alone for sort of half an hour with the data to try and reduce it yourselves. I'll wander around, you can shout at me, wave at me if you have any issues. Then at the end, I'm effectively talking through the steps you should have done, what you should be looking for as you were doing that. Before we start going, we need to make sure that everything is working. So, first thing, make sure that PyWifes, the data reduction software, is in your Python path. Do this, open a Python session in the terminal, python-pylab, and then type import PyWifes. I'll just do a quick question. Is everyone comfortable with Python or completely new to Python? Anyone completely new to Python?
Yeah, ideal.
Better. I converted. Okay.
I mean, it's not that bad. It's just
it's a pretty friendly language, and I will talk through basically all of the commands that you'll need, the Python relevant stuff that you're using. In fact, a lot of it is actually done just from the terminal rather than in Python itself. This first step is simply to check that the PyWise package is somewhere that your Python interpreter knows about it. So when you run the data reduction package, you don't immediately get an error that says, I can't find the data reduction software.
I can't find the data reduction.
Okay. Yep. Are you a Bash or a C Shell person?
Bash.
Okay, so what you're going to do is quit Python. To quit Python, type exit bracket, parenthesis, if you prefer. Not just exit. That always frustrates me. So you want to add the location of the PyWise file to your Python path. So in Bash, that's export Python path equals $, and then for this part, you need to actually add it wherever you've installed the file. So I think that should be there's a code subfolder.
So is it PyWise fold? That's the.
I think that's as far as you want to go. I will just check my machine, what I have.
Oh, and for some reason there's blank spaces in the Wives IFU demonstration.
Yeah, there is. I apologize for that. Wow, that really doesn't show up. Alright. Let's try.
So for this next one,
so if you just make that temp script visible again,
Yes.
So
So
we need
that's
to
what it
rename
goes.
the other thing too, I think we need to rename PyWife's old to just PyWife, right?
No, so PyWife's is the PyWife's old is the folder, so that should be fine. So you want to go as far as the /src. I was trying to make my terminal actually visible for you guys. It turns out number is horrific. I don't know if that has changed.
All the way down to SR, including or just before SR?
So once we end the /src.
Do you have to type export?
It depends what shell you're using. So if you're a C shell, so Bash, yes, you use.
What's
Set.
I believe it's set.
Is it set ENV?
Yeah, it's set ENV.
I tried to import some modules as looking for a file called basic wise metadata of PKM. It's like hard coded, so like /user/install/data.
So that happens when you import PyWise.
Yeah.
That's interesting.
Yeah, I think it's a high code.
My apologies. I will figure out what we need to change to do that.
Yeah, there might be another thing with quotations. So if you go to your Bash profile, Bash.rc, you can just directly write it in there, and if you've already set an environmental variable, you'll see the formatting in there.
Okay, so to solve that problem, in the src folder, there is a wifes_metadata.py file. So, and in there is a metadata definition. So update that to wherever things happen to be in your own folder. So it really probably just be the users. Anything before the Wife's IFU demonstration, you will need to change that. So that should solve the import problem.
Sorry, that's the data folder. Where the data is.
So it's part of the reference data. So it's really just this part that you want
Anything
to
you had before the Wives demonstration.
Yeah.
So the highlighted part.
just in this part. Wifes_metadata.py. which is in the SRC directory.
Change the.
No. Okay, so yeah, I got it working. So
Yeah,
yeah,
so you
this
use
space
slash
won't be able to
slash
you should remove the
data
space.
wherever it is you can forward this file to. So wherever your wife's IFU demonstration folder is.
So you don't have to move it.
It's actually the code.
Yeah.
Sorry?
I would do an open.
It's not with the data, it's with the code, right? It's in that code slash
Yes, it
license
is.
data.
In the code. I was assuming that you haven't separated the code and the data folders, which should all still be in the same subfolder. In YF's IFU demonstration, there should be a code and a data folder.
So I'm working.
Yeah.
So what I did was
So,
I rechanged my IFU demonstration. I did something about it. I accidentally also
just
removed the underscore old in pylons. You don't have to do that as long as it's the system. Then in SRC.
so has anyone succeeded at this part? Okay. Keep going. You have succeeded. Absolutely no
Yes.
problem.
Unless you
Yes,
have
it's succeeded.
You have a QSSH dash X.
There is the. Yeah, that's exactly what you need. Yeah, it's there. I sent the guys here some stuff and they'll review package so we together so I know exactly how to
That was not about
No.
yeah, so you want to rename
No?
Have you guys been talking about rights at all?
Yes, we have.
Because excellent. This is what happened on social media. We're talking about rights.
You should be alright. So, where you are currently, just go to PWD. And then you want to copy that stuff.
That right.
Yeah, that's where you say that. Should be able to the same one if you did the export.
Hands-on.
Yeah, let me just pull that. I'll pull it up.
actually get to the direction.
You guys are working together.
Make sure you get the rules. How we doing?
Oh, okay, no problem. Your hands on. What? Everybody's hands on. Okay with you.
are you sure that that's so far? PW's in there.
You don't learn much if you just hit go.
That's good.
So I think you should just say Python half. Anyone particularly familiar with C Shell? Setting environment variables?
just put the
Set end, no?
Yeah.
But is there quotations or anything like that that you have to worry about?
you
I think you don't put the equal signs. I think it's a space or something.
I'll look it up.
Yep.
Set end.
Okay, so
I don't remember that quote.
That's right.
Yep.
Copy that.
Yep. Actually, Renee put on as well, I believe.
So something like this.
I think it's because you said
If you don't have Python class defined, do something like that. So you don't have to have like, if you already have defined.
It's like over the pipes.
So you just have to define it like this, basically. Say the environment Python path and then just basically the same thing but without the dollar sign and Python path.
Yes, you're right.
Yeah. Oh, I see. Oh shit.
Oh, you
And
never
you're
use all
you're
the
trying to remove the spaces as well.
Alright.
And is assessing that.
Yep, into SRC, and then you have to go into the
Still thinks it's
you have to go into the directory.
space. Maybe like go out and vacuum the folder.
So you go to code and file
It's not gonna know where it is now. It's
you
gonna be like mine.
into SRC. And you go in, and then you have to bin or whatever you use.
So those slashes are just there.
Just a couple of those.
And what's the data?
And
Try the eye.
are you
Oh, it should be.
Yeah, correct. So now you can go back in.
Oh, before you do that.
Hopefully that's
Uh,
Oh, no.
Okay. Yeah, so the one thing, okay, so now that we know it's there, we need to figure out what this bit is, or you can use your local version on that folder. So you can just pick it up before you exit this.
This is
Yeah, so PWD. All the way into highlights code. Everything correct, everything in there. Without the squiggly. Did you get over here? Okay. So without the SRC. You delete everything including by files.
Could you let me know? Yeah, let me know if we could.
Oh, no, it's just cool. Alright, and now it should work. Yeah, boom. In the words of others, should know that.
So people have been successfully typing import pipelines and not producing errors.
Yeah.
Yeah. One second.
Yeah, I have text traces actually on either side of the
It's
I'm trying
off for a little bit.
I will give you
Do anything error like
primary state.
a little bit.
I don't need that.
Does it work? There so
Are you an ideal person as well?
no,
So what was the
no, nothing. Well, 500, but no. Which one? Test it.
Oh, you didn't have your business, but I'll do it, I'll go back here.
I want to do your amazing job.
Actually,
people
it doesn't team up. They haven't put that.
Yeah, that's
Good if you find it.
It seems to be like a
Now the one we
That's
did.
what I
I've seen
so you
I opened this one for the first time.
says switch, indirect.
Well, IRAP, I suppose.
Use
So,
paths to
I was
UA
very low.
the one that
Now you know how to use Pyro.
I've scripted some
So there's a dialog
Some
now
stuff
that's
in
high on
Fire.
the copy that straight over file.
Yeah. I don't use it as
it's
much
used
anymore
as paths
because
used there.
I
So for the UA that you install, like
changed
yesterday used this cache, so it
IRAP
tells
to
you forget everything
this
you did before and
data
you get
reduction
that
group,
package on the second.
which my data
Yeah, that's
so
why I don't have Astro Python installed in
I can't really script that because my data is all work. It does.
Then you need, yeah,
It does. Unfortunately. I think if I would just write a script and then put it in a random data set, then it will just crash.
That is like identify absorption vectors, so there's a lot of like, is that logical stuff?
it's not
But after I did like sort of the first.
Oh, so you're trying to so I use it like just
try to build the spaces.
Like make all these spots, make it easier.
That's the question.
And also just slightly
We just call the previous jack for errors.
I don't know, because you could do it by hand, then I was like, oh my
That'll
god,
be
how much
You just go by and go with that space.
so I need to
Well, so it depends on how much data you have to process.
Oh, it's only
Right.
4 spectra, but
Oh, okay.
but there's a lot of permutations. Because you have no priorities. You don't,
Yeah, I don't know. It's,
That's all because
it would definitely make sense. I was using this IRF package and
Just
after I sort of figured it out, I wrote a script and then I was like, oh, that's easy, I just like enter, boom. But then I had to do a bit more, so I had to not only stack the data, but also correct for.
and then use Python for those
So for that, I needed something else entirely, and that's proven to work, but also it's a lot of like checking your there's like this diagnostic plots that you have to check, and based that you change the small parameters, and it's like I don't see a way of scripting that. Just because my data is pushing the edge of.
Or like, are you using the perspective?
You're talking to a
Yeah, using
person that'd be like, oh, that sounds like a perfect.
might not be able to solve it.
Yeah, maybe.
Okay. I think most people know how this is working. If you're in the minority, I would suggest partnering up with someone who does have it working, and using one functioning laptop rather than a non-functioning laptop, or non-functioning for these purposes. So if you're still having issues, find someone who isn't.
Just try typing my Python.
You probably need to move on to.
Everybody's got a badge.
If you still want to try fixing it for another minute or so, and a few general things to say. So I just want to quickly tell you about PyWifes. PyWifes is a Python, as you probably all now realize, based data reduction pipeline for the WIFES instrument. It was written by Mike Childress. There's a paper that tells you all about it, Childress et al. 2014. It's very good, despite possibly your initial experiences, which are down to Python and not package, to be fair. It's very simple, it reduces the data very well, it does many of the things for you, it's very hands-off, automated, and it provides the intermediate steps for you to check as you go along. You can download the latest version here, which is not Mike's website, but the location of PyWifes. But you should note that we're not actually using the latest version today. Data I had to hand was from 2012. The pipeline and the instrument had changed slightly since then, so we are using a slightly older version of the PyWifes pipeline. So anyone who produced WIFES data previously and had the PyWifes package on their machine, you may run into issues as we go along. And one or two of the steps will be slightly different. PyWaves can simply reduce your data all in one go. You can enter a single, I guess it's 3 commands in a terminal, and then go away for a while, and then have some data queues waiting for you when you come back. But we won't learn anything by doing that, so that's not what we're going to do today. We're going to reduce things one step at a time and check the data as we go. Before that, a very important thing when you're reducing any data, before you start reducing it, to check your raw data. As computer people from the 80s like to say, garbage in, garbage out. If your calibrations are not good, if your science frames are not good, if any part of the stuff you're putting into your data reduction process isn't good, it's going to come out bad. Not only will it come out bad, it'll make all of your other files bad. If you have a saturated bias frame, or something called a dark frame when someone turned the lights on accidentally, then you subtract 65,000 counts from all of your science frames, you're not going to have many counts left at the end of things. Check your raw data. Most of the time you would be doing this as you're observing. Depending on the instrument, that may not be an option. Q mode or someone else may have taken the data for you. Most of the time you don't need to check every single raw data frame. If you've taken a stack of 20 biases, you probably don't need to check every single one of them. If you're very keen, then you can do so, and it will probably make your data slightly better. But if you have better things to do than look at 20 bias frames, then looking at 1 or 2 is probably okay, because they're generally averaged during the process as well, median. There are various things to look out for. Saturated exposures, I mentioned, is a very common one. So a saturated twilight flat frame, you put in the wrong exposure time for an arc frame, something like that. Another favourite one with astronomers, files like that aren't what they claim to be. So WIFEs will automatically recognise the kind of file based on the header keyword. The header keyword is set when you're observing. You basically click a button and say, I'm taking a flat frame, I'm taking a science frame, and this writes something in the header. At 3 AM, it is very, very easy to forget to click that next button, so your arc frames are labeled flat, your biases are twilight frames, your science frames turn out to be darks, all sorts of things like that. So check the header keywords, check what WIFE thinks the file is, make sure that they're actually the same thing. That's relatively easy to fix. You could just manually change the header keyword in whatever your favourite fits editing program is. But make sure you do that before you start the reduction process, not after you've reduced your data or thrown an error from the pipeline. You can also have with WIFEs in particular, there's a button to essentially put in the wire mask that I talked about, the step that's used to calibrate the X and Y positions of your spaxels. It's very easy to forget to do that when you think you have done. Label the frame wire, write down wire in the log, but there's no actual wire in there, or the other way around, leave the wire in when you think you're taking it flat. So look at the frames as well. Make sure that the frame looks like the kind of calibration that it is claiming to be. Exposures with no or very low flux. My new favourite way of screwing up data when observing with SAMI is to do our evening calibration frames and forget to open the mirror cover. Unfortunately, the lamps are bright enough that they get a reflection off the back of the mirror cover, so you do get some photons in our flat frames, but you get 100 or 200 rather than the 2,000 or 20,000 that you expect. So again, check the data, make sure it looks like what you expect it to look like. Again, that's something you ideally want to fix when you're observing. You probably need to open the mirror cover at some point to get useful science data, but if it hasn't been fixed while observing or somebody else did the observing, exclude that file from the data reduction. Don't try and use crappy calibrations, because they will give you crappy data. Excessive amounts of cosmic rays, so very long exposures. Something people like to do, though I'm not a personal fan, is when it's cloudy and you're halfway through an exposure, rather than just giving up on it, pause the exposure, wait for it to stop being cloudy. If you wait too long, you end up with a CCD filled entirely with cosmic rays, which is no use to anyone. Just get rid of it. Don't try and process crap data. Weird artifacts. CCDs do strange things sometimes. Sometimes the controller software breaks. Sometimes an afternoon tech will walk into the instrument room and turn the lights on when you're doing a calibration frame. Sometimes there will be a mysterious LED in the instrument room that has not been turned off as it's supposed to be. These things ruin your data. Look at your raw data, make sure they're not there. If they are, get rid of them. Remove them before you start the data reduction. So Normally when you start reducing wife's data, the first step is to get it to figure out what all of your files are. Now, I've actually done this for you to make life a little bit easier, but what you first do, there's a couple of pipeline scripts that are described in the README that essentially open your FITS files, look at the headers, see what the header says a file is, then creates a table effectively that says this file name is of this type, this file name is of this type, and then it uses that information for the rest of the data reduction process. There's one terminal script that just basically creates a human readable version of that, and then there's a Python script that turns that into what's called a pickle, which is a Python way of packaging data, essentially. So a file that the Python will play with. You can edit this manually, so you can either take out crappy calibrations, remove them from the reduction folder so they don't get added at all in the first place, or you can remove files at that point. You might only want to reduce a subset of your files at this stage, so edit the file there. As I said, I've already done this for you. You can have a look at this yourselves. So the relevant file is in the data folder, and there is the savebluemetadata.py script. So this is the output of just a terminal command. You'll see that it's a very simple program that will just have file names, and it'll tell you what kind of file it is. So if you wanted to manually edit this, you could delete one of the files from here, so it can just get rid of this one, say, if we don't want to use it. We might want to use a specific one of our arc frames, for instance.
I lost track of which file it is in your.
So this is savebluemetadata.py.
So that's the file that will be created after you
Yeah.
have this.
Yes. So it's in the data folder. So that's the first file that's created. Then you run that in Python, and that will create this wifesd.metadata.pkl file, which is the sort of Python readable version of that, which is not very human readable, but essentially contains the same information. You can see there are the file names in here. It's telling you what kind of file this is here, so it's a wire, and then there's some other stuff that's a bit less human readable, but Python understands. So it's just the sort of the Python version of what's essentially in this savebluemetadata.py.
When you open, I just don't have any experience with pickle files. When you open them and back up, you don't need to know the dimensions and labels of the. It reads all that stuff in it.
Yes, it does.
Header. Okay.
Yeah, it stores the array information as well, so the array structure is stored as part of that.
And labeling?
I believe so, yes. With PyWifes, I would always recommend editing the savebluemetadata.py file and then rerunning it to create that .pickle file, rather than editing the pickle manually. If you're super keen, you can check the pickle to make sure that what's in there matches what's in the Python file, but in my experience, it always does. So don't worry. Yeah, that's a relatively straightforward step.
And you just, if you want to do that, you just put a R instead of W in the open call.
If you wanted to
Read it.
yes. Or you can open the pickle in a text editor, actually.
Oh.
Yeah, opening it in Python, you open the file with R, but then you also have to call pickle to interpret it. So
it's not a binary file?
No, it's not.
Oh.
Okay, so now we're going to get onto the actual data reduction part. So the data reduction part is done in this reducedbluedata.py file. This is in the reduction scripts folder, which is in code, ITSO reduction scripts. So we have reduce blue data. So the stuff at the start here is just opening the metadata file that you created. And this is the bit you want to play with. So anything from the user reduction design is set here, section. So this section is describing all of the reduction steps that the pipeline is going to take. You can see it says step, overscan, superbias, bias, sub of the various steps. Then there's a run section, which will mostly say false. I believe it should say false everywhere for you guys. I was playing with this earlier, so I need to set these to
Is this in the code subdirectory?
in the code subdirectory and inside reduction scripts.
Reduction.
I'm just going to set all those to false. There's a few other extra arguments for some of these steps. So there's a suffix, which comes up quite a lot. So that will tell you what the reduced file that step is going to create. So it'll take the incoming file name, it will add that suffix to a file name, and it will produce that as an output step. So things produced by the overscan substep will have a 0, 1 suffix, things produced by the bias subtraction step will have a 0, 2 suffix. A few of the other steps have some additional arguments. You can see, say, for example, in the super flat step, it'll say source twilight, so it's twi, so that's using twilight flats in that step. In the next one, it's using dome flats, for example. Scale median 0 is just telling you how it's doing the averaging. So there's a few different parameters you can set. My experience is you don't need to change these very much. If something is going not very well, then revisiting these arguments is something you may want to do. But to get the options here, you probably need to dig a bit further into the Python available in each, that is actually sort of being called by each of these steps. For a person who doesn't particularly want to do that, then this just set of commands here that are on my screen is all the things you need to edit. So before we close this file, yep.
Would you mind if would you be able to go into full screen and then kind of like making things very because I don't know, maybe it's my eye, but I can't really see.
Yeah, it is kind of annoying.
That's what it's like. Well, no, you can have it.
That was blurry.
Just want to zoom in full screen. See if I can just zoom anyway. It really doesn't want to do.
Apple Plus doesn't work?
No, Apple Plus isn't working. Might be an Xcode thing.
Oh, you're using Xcode.
I am using Xcode, I apologize.
Oh, no, sorry.
I do have the same stuff on here as a screenshot. Is that slightly easier to read? Is that slightly easier to read on the Python presentation? So this is just a screenshot of the same stuff. Okay. So everybody hopefully has that file open. What I want you to do is edit next to overscan sub, run to be true, which is what's written here. So just change the false to true, and then save the file. Yep.
It's
No, there's only three.
yeah, but it's changing.
How are we doing? Everyone happy with this step so far? Overscan some? See some puzzle blocks. Okay. So what we've done now is we've said when you execute this whole reduction script, I want you to do the first step in the data reduction, but no other steps. Everything else is set to false. So all it's going to do is run this overscan substep. So the way we execute the reduction script is we go back to our terminal and we type this command here. Can people read this? Perhaps not. So this says Python. So when you execute this, you want to be in the reduction scripts folder. So cd to wherever that is on the terminal. Then we type Python, reduce underscore blue underscore data.py, and then you need to give it the path to the metadata.pkl file. So in my case, this was tilde/data/wife's /IFU /demonstration/data/wife's b_re_metadata.pkl. This stuff should all be the same for you, so it'll only be stuff.
So this is the Weissman data that we changed the paths to?
No. So this is the file we were looking at earlier.
This isn't data. No, that's it. Oh, yeah. This is a .pkl?
The .pkl.
Oh.
Maybe this one don't have this
I was just adding the thing to focus on how do you do it every time you want it. If you do want this and you also tell me about it, you have to redo it every time you want. But if you put in a file like that, every time you run the terminal, it will always put a file and store activity. Yeah, I can put anything there.
Just running your regular terms.
No, we can do that from the terminal directly.
Do you get out of Python?
What's that?
Yes, leave Python. Leave Python and run this from the terminal.
But then it says no what.
Yeah, then it doesn't load the module instead.
Does it not? If you open a new terminal session,
Yeah.
then check your Python path.
We can just like symlink everything into that directory.
That's true as well.
Oh, I just let sense Python path without. Yeah, that's worth. Yeah, without post, sign back.
So what I did is I went back, and because you're starting a new terminal and it's not in your batch profile, you have to redefine your path. So I just really went back to the one. Oh, because you didn't use
No.
because you didn't use
Is that working for anyone?
I get an error where it refers to your original location, but I don't know what script that's supposed to be.
Where is that?
So it's
Does it tell you which file?
I assume it's the.
Okay. So yeah.
It's reusable data.
no such
Yeah, so it's possible.
Oh yeah,
That's in there. Let me have a quick look in those files.
Yeah, that includes your.
Yes. So one other thing we need to change that has been pointed out to me in that reduce_blue_data.py folder file. There is a hard-coded path to where I would like the data to be saved. So there's a line 18 is approach to equals something. So that's a path on my machine, and you want to change that to a folder on your machine where you would like the reduced data, where the data exists, and then where you would like the reduced data. In fact, you probably only need to change that line 18. The other ones are relative paths. Should be fine.
Yeah, so that works.
Okay.
Yeah, that
So that is now producing an output for you.
So what's that supposed to be?
So in the reduced folder, so data/reduced, you should now have a bunch of files that end P01. Yep. So these are the outputs of the overscan subtraction step. So I would recommend opening those in DS9 or whatever your favorite fixed view is, and having a look at those files. So the first one, quite boring. That's a bias. There are more interesting ones further down. So 137, for example, is more interesting.
137, that shouldn't be a problem.
Yeah, I believe 137 is 9 flat.
There's some line in it.
171, 173 is.
The Galaxy, yeah. So there's also a text file in the data folder called description of data, which tells you what each of the original frames was. Did you get anywhere? I would recommend tuning in with one. Yeah. So people are getting that step to work.
Yeah, it's a spectrum, right? Or a series of stack spectra.
So this is all raw wipe samples. So all this first step has done is wipes data is arranged in such a way that part of the CCD is never ever exposed. It's left blank. So effectively, overscan sub is doing a bias subtraction. So it's a bias based on each individual data frame. There is another bias subtraction where it's taking the bias value in the correct CCD location away from each CCD.
Why is there seems to be like a
There's curvature in this.
curvature?
Yeah, that's typically very standard for instruments.
Is that worrisome? Because there's not a. Does that imply that there's a nonlinear response to wavelength solution?
No, it's not worrisome, but it does suggest that certainly. But that's calibrated out. So your wavelength solution, what you end up doing is you fit a polynomial to each spectrum, effectively. No, it's almost, my experience in instruments is it's always a polynomial. People don't worry too much about what your sort of lambda to CCD XY conversion is, as long as it's a number that you can find out.
Yeah.
Okay, so hopefully people have figured out how the PyWise pipeline works in general. Now, I am going to stop talking to all of you, possibly go around people who are struggling. The rest of you who have got that far, I would suggest go back into your reduced blue data script and start running some of the other reduction steps. So, if you're feeling keen, you can set everything to true and it will work. It'll take a while, but I would suggest doing them one at a time and taking a look at each of the subscripts as they're produced. So you relate that to the step that's been
So you're saying
taken.
there's no prize for winning?
There is no prize for winning. There are prizes for understanding what's going on and pointing out issues. The prize is that your data reduction will be better in the future.
It's the
There's no
worst prize
actual-
ever.
Well, it could mean that you write a good paper
It's not
and
edible
like the
or
job
anything.
in the
Wait,
future.
the prize is like the pride we feel inside of us?
Yes.
I've gone wrong.
Would you recommend that we do each step on its own?
I would recommend that the first time, yes.
What do you
There are one or two you can group together.
The big words.
Like the ones that are already grouped together?
Yeah, so actually, anything that doesn't have a suffix, I would suggest grouping by suffix. So you'll see that between suffix 2 and suffix 3, there are a bunch of steps that are grouped together. You can probably run all of those out. They're producing calibration files generally. So run them all together, and then they'll produce a few independent outputs towards the end. Okay. So, who has been struggling still? How far have you got?
Well, we found why it's just my
I think okay, the next episode, what I assume that these were. Yes.
So I missed everything you said.
How did you do that?
You move Python from 3 to 2. I have to because this code fails in Python.
You need to, by using,
Yes.
how did you install Python? And I do that.
Essentially
Came with
That's okay that I'm in a different installation.
Oh, this is
You do anything.
So this will just edit the file, it will save the file, and then when you run it from the terminal, it will just go and look at the source file. It doesn't matter where you edit the source file from.
So let's just run this.
No. So what we can do, I just want to So this stuff is
Correction
just
stuff doesn't change.
metadata, it's already been saved, and that's just telling you the pipeline what the files are, basically.
That's Twilight.
So the real reduction stuff.
That's somebody dropped the water.
So each of these is the steps. So step, whatever. And the steps of the pipeline is So what you could do is if you see one that sets a false for all of these at the moment, so you can do it. So you can learn
I think that's wise.
So,
Did you turn any of the other options on?
So now when we call this script, it likes if you're comfortable with your data, then you can almost just set it true, run it, go away, and come back and you'll have some reduced data again. If it's the first time with the data, or for the purposes of this exercise, I was just doing one at a time and then I was output. Okay, so
that's what other people have been doing. They've been running, changing this script.
we say so
Right, let's
execute by
Python,
do you want to find the
So basically, I think if you
stuff? Is it?
like specify set just going back.
Oh, in the
Specify
so
Python
you
to
Oh,
set it to
right.
run. So you can install packages there. Check that.
Is that right?
Pip is for 2 and Pip 3.
Alright.
Yes. I keep getting it.
This is the thing you're opening.
I didn't see any of these features in Twilight. The water stuff.
Oh, did you just change the...
Yeah.
Oh, right, no, I didn't.
Yeah. Yeah, there it is. There's no numbers in it because
Some of this is certainly the latest.
25.
Super single stripe. Python just tells Python that this is the program we use. This is the execute the script, and then execute it to where our data is.
Works for other things. Well, Pip.
I just see...
You said the ones that you already.
So you're at
false.
Terminal.
So
it's
yeah, I know.
Then you start from the beginning all the time.
It's running that.
Then you start from the beginning all the time.
That works.
Sort of like a strongly possible.
File intermediate reduction step file where it's executed the first step in the pipeline process and then it's reducing the output at that stage.
Oh.
So to execute the other steps, we go back and look at the production script file and just set the
I could see it.
So look at it, or just
If you have,
yes, no.
yep, absolutely. If it's set right, I just don't put it in. So
Books
each
submitted,
of
or
the four
course
data
paper.
files,
Yeah.
it's
Well,
produced
she submitted it. It got
that
rejected.
file
Submitted
that
to
the
another.
first step,
True.
by the way,
So another
releases.
rejection.
It's a very
No,
uninteresting
she
step.
submitted it
It's
to
really
the
not to track the
So I
bias.
can't access
Got
something
accepted.
now.
The
It gives
other
me an
steps
error.
So she's having a
Okay,
full-on
please.
panic
because
attack.
when you
Yeah.
install packages, it's not
She-
like binary
did she
expressions.
change it?
It's compressed.
Yeah.
In the interest of time, I might talk you through the steps that you may have just executed or may not yet have executed, just to give you an idea of what the outcome should be. So the step we're executing to start with, the one I kind of talked you through, over scan sub and up to bias sub, are all essentially subtracting the bias level. They're just doing it in two different ways. You might notice that as an intermediate step, a bias file is created in the reduce folder. So what's it's done is it's taken all the bias frames and it's just averaged them to create a super bias, a high signal to noise bias frame. And essentially the overscan region on the edge of the CCD is subtracted from the file, and then the bias frame is subtracted from all of the other files. So this is just to remove the bias level on the CCD. It's worth checking the combined bias frames, certainly. Median over a decent number of biases should mean that that's largely artifact-free. If it isn't, then you may want to go back and look at the individual biases and see if a large number of them are damaged in some way, disable the crappy ones. If all of them look terrible, that's probably something you should have noticed when you were taking the data. But in all honesty, one other thing I haven't mentioned about the WIFE pipeline is you can skip steps. So you'll notice, certainly in my version, possibly in your version of the file, some steps down here are commented out, so that'll tell it to skip those steps completely. Normally, you won't be able to execute a step unless the previous step has been available. So say I wanted to do my bias subtraction, but I hadn't done my overscan. The pipeline will say, well, for this one I want a file with a subscript P01. None of those files exist. I'm not doing this until you've made those files. If you wanted to skip a step completely, rather than just not run a step now, you have to comment them out like this down here. So that's just a useful way of using the pipeline. So next set of steps, these things in the red rectangles are essentially flat calibration steps, so correcting for the CCD sensitivity and the illumination correction. They're done by creating what's called a super flat, so taking all of the flat observations, averaging them to create a high signal to noise one. That's processed slightly to try and separate out the illumination correction and the CCD response. And then further down here, later on in the process, that's applied to your data.
Just a quick question on the dome flat. The NPF, because when I first clicked on it, I think it was all of a sudden I was like, why do I have a single? Okay, so that's because it's stacked in extensions?
Yes, that's correct. So what WIFE does, and that's this next step, spectral extraction, rather than say something like 2DF. Have you guys had any 2DF hands-on experience? Okay. So what 2DF does is it creates what's called a row stacked spectrum. So a raw 2DF frame is 4,000 pixels by 2,000 pixels. That's just the CCD. A processed 2DFDR frame is 891 pixels by 2,000 pixels. So each of those 891 in one dimension is just a fiber. So it's fiber number by wavelength rather than CCD coordinates by wavelength. So that's one way of doing your intermediate spectral extraction. WIFE doesn't do that. It extracts each slitlet, each 1D spectrum, or long split spectrum to its own extension, which is why the MEF multi-extension fits subscript appears on lots of data reduction steps. So that's what this spectral extraction step is doing. It's creating the slitlet profiles here. It's fitting to a flat frame. It's looking for the slit edges, so when the flux sharply declines. How it does that exactly, there's an edge finding algorithm, and it looks for a set amount of flux that's just hard-coded. Once it finds the edges of those slits, it creates a map. effectively it says that this detector pixel, from this detector pixel to this detector pixel, you are slit at number 2. From this detector pixel to this detector pixel, you are slit at number 3, and so on. Then in this slitlet MEF stage, it applies that map to to a set of your data frames that are going to be used for the future reduction steps and converts those into multi-extension fit styles. So each of your extensions is now a single long slit spectrum corresponding to a single Y pixel and all of your X and lambda pixels for that Y pixel in your data cube. As a minor note, specifically for this version, the calibration frame created on this step is called slitlet_depths.fits. In the 2012 version of the pipeline, that's a lie. It's not a fits file, it's actually a .pkl file. In the current version of the pipeline, that is correctly labeled as a pkl file. So when you try and double click on it and DS9 says, I can't open this, DS9 is right, the file is wrong, and you can open it with pickle in Python if you really want to look at it. But it really is just a list of start coordinates, end coordinates, and slitlet number. Okay, next step, wavelength calibration. So in the wavelength solution, so on each of your multi-extension slits that have been extracted, 10 minutes, yeah, should be alright. It will extract the arc spectrum for those slitlets. It will find the peaks in that spectrum. It will compare those peaks to a known line list. Again, the lamp, I believe, used for this calibration changed between 2012 and 2016. So the new version of the pipeline will screw up your wavelength calibration on this older data. Similarly, the old version of the pipeline will screw up your wavelength calibration on the newer data. So check you have the right line list for your epoch of observation. And then this will create a wavelength solution.fits image. You can check these if you want. They're not super informative, but what you're really looking for here is, again, it's a multi-extension fits file where each pixel in each file corresponds to the wavelength value of that pixel in the data. So this should vary smoothly across the CCD. You're not going to see discontinuities. You shouldn't see discontinuities. You shouldn't see sharp jumps. You shouldn't see steeply changing gradients in this file. If you see any of those things, that means your wavelength solution has probably gone wrong somewhere. The way to solve that, you can tweak some parameters in Wife's data reduction. What I would suggest doing before that is see how many arc frames you have, see if it's a problem in all of them. If it's not a problem in all of them, use the ones that are good. Don't spend a long time fiddling to try and get it to work. Wavelength solutions can be very sensitive to a couple of input parameters, so finding the ideal solution can take a while. So find some good ones if you can, disable the bad ones.
So it automatically says no, like, how do you try to track the
No, it's automatic. Yeah, you don't have to click on peaks or anything like that. So the pipeline is very automatic. As I said, you can literally just set true, go away, have some coffee, get to dinner, get drunk, come back in the morning, and then you'll have reduced data. When you're running that step, I don't know if any of you guys have got that far, but you will get the terminal output, which you cannot read at all on this screen. The output you get is a... Can I read this? So it'll say deriving wavelength solution from the arc frame that it's doing it for, and you get a... for each slit, you get a, I believe that's a dispersion, a pixel, a central pixel value, and a start and end wavelength value. Those numbers should be quite similar from slitlet to slitlet. So if one of your slitlets has a dispersion that's 10 times the value of the other slitlets, something has gone wrong. If your start wavelength is hundreds of angstroms different to from one sletlet to another, something's gone wrong again. So there's quite a lot of information there. You don't need to you don't have to look at the raw file or the wavelength solution file there. Most of the information you need to decide if that's correct is actually given to you in the terminal. Wire solution. I talked about this a little bit. This is the step where a physical mask has been placed in the image plane, and there is a dip that's a constant x value, and it fits to that value. I might show you the output for this one because it's kind of counterintuitive. It's probably not what you're expecting to see, but it's actually a very, very helpful. So this is the Y2P wire solution frame. So this is a 2048 by 25 frame, and I believe there's one per.
The dark.
And there's only a single one of these. So what you're looking at here is the x-axis is wavelength, the y-axis is the y spatial axis, or effectively slit-lit number, and then the value of each pixel here is the fit position of the wire in that particular slit-lit. So again, these values shouldn't vary very much. They should be quite similar. You might notice this one has a fair amount of structure. This one down here has a value of 18, whereas it's typically 20. It also looks like something might have gone a bit funny here as well. Again, solving this, ideally find a better wireframe. Find a frame where it's worked reasonably well. You typically only need one of these per night with wipes, so take a couple. One should be good. Again, if you still can't find a solution, there are some parameters you can fiddle with. You can even go in and do this step by eye and manually edit that file if you need the wire solution file if you have to. It is something I found with earlier versions of Pipeline, and it's not necessarily well done. Generally what's gone wrong though is you probably saturated your wireframe or not had enough counts in your wireframe on that particular exposure. So the better solution is to find a better wireframe. Okay. Next step, this is simply applying the flat fielding and also removing the cosmic rays. Again, I find that it uses the LA cosmic routine, which is pretty standard in astronomy. There's C versions, Python versions all over, often come packaged with data reduction packages. Really, it's looking for clustered pixels with very different fluxes to the surrounding pixels. This is something I think that is not perfect about the WIFE's pipeline. So it applies this step after it's extracted all the slitlets. I think it should apply this step before it extracts slitlets. This is because cosmic rays don't care about your slit-lit structure. They hit your CCD. So cosmic ray can cross slit-lit boundaries, which actually makes it easier to detect them on the CCD because they are a single contiguous structure there, whereas if you've extracted slitlets, you might have got half a cosmic ray or a single pixel on the edge of the cosmic ray. One pixel isn't something that normally gets flagged as a cosmic ray, but if it's a whole chunk of pixels together, then it's much easier to identify. Unfortunately, unless you want to do a lot of Python coding, you can't tell WIFE to do this a different way, but it still works pretty well. It also applies the flat response that was previously calculated. If you've already checked that, then nothing is going to go wrong at that stage. Okay, so cube creation. What happens at cube creation, which is CubeGen here, is it applies. Yes, sorry.
Which files does it flag for the cosmic rays? Because currently it's running, like I said,
yeah, the cosmic ray takes quite a while.
But so it was flagging the 171, 173, so it's size exposure.
Yep.
Now it's switched to 136.
So I believe 136 is the standard one.
Oh, right.
So yeah, so anything in the way you observed an actual astronomical object, it should flag at this stage. It's been out of finish shortly, so I'm going to hurry up. Yes, so CubeGen. Again, this is slightly counterintuitive. So what WIFE does is it applies the wire and the wavelength solutions to your multi-extension fits files, but it does unfortunately leave them as multi-extension fits files. So it puts them on a common X scale and a common lambda scale, but it keeps each sort of Y pixel, Y column as a single fits extension. This has changed in the latest version of the WIFE pipeline. There's an additional step, which is something like create 3D cube, which actually creates the kind of file you expect to have, a 3D data cube. But in the 2012 version, it didn't do this. For your convenience, or just to, it's much, much easier to interact with 3D data cube than a whole bunch of multi-extension fits files. I find. So I wrote a little Python script just in the wife's utilities file that just does this for you and produces a 3D file. You can execute it with this command in here, or this set of commands. The slides will be available after this, so if you guys want to go back to this step later on, then this will be available for you to follow. And then once you've made your cube, you should certainly look at it in QFITSD. So why don't we do that? So I made a cube called NGC1336. I could open it in DS9, but I'm not going to, because DS9 isn't great for cubes. Instead,
where is the cube?
So the cube is a separate step that's not executed by the wife's script. So that's an additional Python command you have to run with the 2012 version. The 2015-16 version, that's not true. It actually does it for you.
Which script is it?
So it's the wife's utilities. It is this set of commands here. So you have to do this one in Python, unfortunately. Go into Python, import wife's utilities, and then it's wife utilities.wife's multi-extent NEF to cube, and then you have to give it the path to the file that you want to turn into a cube and a path to a file that you would like to make as your cube. The one thing it does is that it saves the signal or the flux. So if you're familiar with multi-extension FITS files, the cube doesn't actually save the flux as the first extension, it's the second extension. So you do have to fiddle with that a little bit. So this is our data cube. This is our galaxy, this is a foreground star, and in QFITSView, when you hover over any pixel, you get the spectrum. You can extract the spectrum, so this is our galaxy spectrum. Calcium H and K, H beta, NGB, I'm making that up. H beta, NGB, some ion lines over here. Not much in the way of emission, this is a cluster early type galaxy. If you're familiar with cluster early type galaxy spectra, you will know that the continuum in this doesn't look anything like an early type galaxy continuum. It should be steep here, relatively flat here. So that's because we haven't flux calibrated this data yet. The last few steps of the pipeline are the flux calibration step. Again, I'll let you guys get to that in your own time. So the next slide is all about that. There's some more tips and tricks in the slideshow, but for now I just want to get to the closing remarks. So integral field spectroscopy is an extremely powerful technique. It's become extremely popular over the last 15 or 20 years, and it's really revolutionized many aspects of modern astronomy. Different IFUs do very different things. Some work in near infrared, some work in far blue, some work in the optical, some have very broad wavelength ranges, some have very high spectral resolution, some have large field of views, some have small field of views, some work with AAO, some are on 2.3 meter telescopes, some are on 10 meter telescopes. There's an entire zoo of IFUs out there, so don't just sort of pick the first one that you come across. Make sure that the IFU you choose for your observations is the correct IFU, the one that's going to give you the best science returns. The instruments are complex because of this problem of taking 3D data and putting it on a 2D CCD, and the data is complex. You've seen the data reduction process has many steps, 2 minutes, and that means that your data is also complex. Data is correlated in interesting ways. We didn't talk about that very much, but there's overlap from adjacent fibers, so spatial pixels are not independent. There's also wavelength correlation, there's correlated noise in these. So the data themselves is complex. The only way you really understand that is by reducing data yourselves. Different IFU designs come with different pros and cons, so think about that when you're choosing the IFU you want to do your observations with, as well as when you're reducing the data. And my final two tips are, many IFUs have really good pipelines, so they're complicated, but somebody's already done the hard work for you, in the case of WIFEs, SAMI, Sauron, for example. So if you can choose an IFU that already has a pipeline, if your IFU doesn't have a pipeline, find somebody who's already reduced the data and get them to do it for you. Tackling a complicated IFU for the first time on your own is a very challenging, very, very time-consuming process that is going to generate more tears than good data for you. So collaborators or pipelines is my final recommendation. Sorry I overran, guys. Hopefully this has been useful to you.
I think that's pretty much what I was loving.
Okay. Well, I did overrun because I skipped like 10 slides.
Right.
But you can look at those on the web. Or come ask me any questions you have. Is it a coffee break now?
Yeah, it is.
Yes.
Coffee break.
Okay.
Okay, thanks, Nick.